We are continuing to work through our final review worksheet. In this video, I'm going to be working all the problems on page 5. That's numbers 17 through 19. 17's easy, 19's pretty challenging. So here we go. Given the function f of x, find the following. F double prime of x. So we need to calculate the second derivative. Now, to get the second derivative, we got to go through the first derivative. So begin by finding the first derivative of f. It's simply a polynomial, so we can differentiate term by term using the power rule. The derivative of 2x to the fourth is 8x cubed. The next term is negative 6x squared. And finally, negative 4x. Once we have our first derivative, we can get our second derivative. So we just, again, differentiate term by term. The derivative of 8x cubed is 24x squared. Next term has derivative 12x, and finally, minus 4. So the second derivative of this function is 24x squared minus 12x minus 4. Part B says find f double prime of 5. I just have to interpret this notation. It says go to the second derivative and plug in 5. So everywhere I see an x, I'm going to replace it with 5. And then calculate. Now feel free to pop this stuff into your calculator. It's a good way to avoid those simple little arithmetic mistakes that we all make sometimes. So we had 24 times 5 squared minus 12 times 5 minus 4. And we end up with 536. Remember, you can check all these answers in the answer list at the end of the review worksheet. Moving on to problem 18. I hope you thought 17 was a piece of cake. Moving on to 18. Consider the function f of x. Find the following. The intervals where the function is concave up, part B, the intervals where the function is concave down, and part C, the inflection point. In this problem, we're going to be making a sine graph. We're going to be setting a derivative equal to 0, and we're going to be determining where that derivative is positive or negative. It's going to feel a whole lot like the first derivative test that we applied on problems 14 and 15. The only difference here is that I'm using the second derivative as opposed to the first derivative. Same process, just applied to the second derivative. So remember, if the problem says, where is the function increasing or decreasing? I analyze the first derivative using that sine graph. If the problem says, where is the function concave up or concave down? I analyze the second derivative using the sine graph. Okay? So, first of all, we need to get our derivatives, right? Let's just pass through the first derivative in order to get to the one we need, which is the second derivative. Can you tell me the first derivative? Test yourself. What would you end up with? How about negative 12x squared? 36 times 2 is what? 72? Plus 174, and the derivative of 9 is 0. Now, pass through to the second derivative. That's the one I'm interested in on this problem. It is essential that I get these derivatives right. If I mess up on my derivative, I'm not going to be able to give the correct intervals of concavity. So take your time and differentiate carefully. So, second derivative here would be negative 24x plus 72. You might find it easier to factor that derivative when we set it equal to 0. Notice we have a GCF here, greatest common factor of negative 24. Let's rewrite this as negative 24 times x minus 3. Okay? So what did we do? We found the second derivative. We set it equal to 0. Now what will I obtain if I solve for x? I will obtain not a critical value, a potential inflection point. Okay? When I'm looking for intervals of increase, relative maximum, relative minimum, I set my first derivative equal to 0 and solve for x, right? When I'm looking for intervals of concavity or inflection points, I set my second derivative equal to 0 and solve for x. So at x equals 3, I have a potential inflection point. Let's go ahead and construct our sine graph. Just going to use this workspace here. Like we did with our critical value, we're going to put our potential inflection point on this number line. It divides it up into two sections, and I'm going to examine the sign of the two factors of my second derivative. Two factors, yep, two factors. Remember, the negative 24 affects the sign of the derivative and the x minus 3. So I'm going to list both of my factors over here. Now, easily, negative 24 is negative no matter what interval or test point you're using. So we really need to examine x minus 3. Let's choose a test point to the left of 3, any number left of 3. I like 0 because it's easy to work with. If I plug 0 in for x, I see the result is negative. Remembering that our second derivative was composed as the product of these two numbers, a negative times a negative is a positive. So my second derivative is positive on that interval. Now let's choose a test point to the right of 3. How about 10? 10 plugged into my factor gives me a positive result, and we know a negative times a positive is negative. Okay, so my first derivative tells me increasing, decreasing. My second derivative tells me concavity. Concave down occurs where your second derivative is negative. Okay, so clearly that's the right side of my sine graph. So from 3 to infinity, our curve should be concave down. Okay, zip back up here to 18a. Where is it concave up? A function is concave up where your second derivative is positive. Our second derivative is positive here on the left side of our graph. So if I find the leftmost point of that interval, clearly there's not one, so we call it negative infinity, up to the rightmost value there, which is 3. Okay, so our graph is concave up and then concave down. This is a cubic polynomial, so it's probably going to do something like concave up and concave down. There will be an inflection point right there in the middle. Okay, so concave up on the left side, concave down on the right side. You can certainly type that into your calculator and inspect the graph. The inflection point occurs when your graph changes from concave up to concave down or vice versa. So it's sort of like a bend in the graph. Clearly, this occurs at x equals 3. So I know the x value of my inflection point is 3. I just need to find the corresponding y value. How do you get a function value? You always go back to the original. So to find the y value of the original point on the graph, I'm going to plug 3 into f. So replace all of the x's with 3's. How about we type this one into our calculator? I'm not going to attempt to do that one in my head. So we have negative 4 times 3 cubed plus 36 times 3 squared plus 174 times 3 minus 9. We end up with 729. So at the point 3, 729, we would be able to see that bend in the curve. All right, now 19 is pretty challenging because it's long, but it's going to put this into perspective. When do I analyze the first derivative and what information does it give me? When do I analyze the second derivative and what information does it give me? Now, you're probably going to need more space than what we have right here. So you might want to work on the back side or get yourself a piece of notebook paper. 19 says, carefully construct the graph of the function f of x. State the requested information and clearly draw the graph in the space to the right. Let's begin with the domain. Notice f of x is a simple polynomial function. The domain of every polynomial function is negative infinity to infinity. To find the y-intercept, we set x equal to 0. If I set x equal to 0, the only term that's going to have any value is this last one. Those first three terms would zero out, giving a y value of negative 2. So when we set x equal to 0, the y value is negative 2. Well, we've got a point on our graph. We are making progress. Now, as we go, I'm going to try to keep up with our cumulative information on a carefully constructed graph. Always, always, always label your axes x and y. Put your arrows on the end and clearly indicate a scale. Okay? So we can go ahead. All I know so far is my y-intercept is 0, negative 2. So I'll put that on there and label it. All right, so we got 1 point down. Next, we need the critical points, the interval of increase, the interval of decrease. Okay, so all of these involve the first derivative. So I'm going to flip over and get a little more space here to work with and find our first derivative. So looking at our function f of x, the first derivative would be what? Negative 9x squared plus 12x minus 4. Do you feel pretty comfortable with your derivatives? Especially with polynomials. Nothing fancy like a quotient or a product rule. Now remember, in order to find critical values, what do we need to do? Set our derivative equal to 0. And then solve for x. We should attempt to factor this problem. Now, it might be easier to factor it if we have a positive leading coefficient. So let's begin by taking out a negative and see what we're working with. We'd have 9x squared minus 12x plus 4. Observe that this is a perfect square trinomial. So it would factor as 3x minus 2 times 3x minus 2, or 3x minus 2 quantity squared. If I set that factor equal to 0, it's going to count twice. Will be a double root. We end up with our critical number. Our critical number here is 2/3. What that means is if there is a relative maximum or a minimum, I should check 2/3. It does not mean that it's guaranteed to be either one. So we have found the critical points. We've got one of them. X equals 2/3. Remember, that's what divides our number line up, so we can check the sign of our derivative. Let's go ahead and construct our first derivative test or our sign graph. So we'll take our only critical number, 2/3. We'll put it on our number line, and we're going to check the sign of the derivative on each interval. Now, if you're really paying attention, this is not going to be a lot of work. The only factor that I have here, if I write it like so, just the entire derivative, is a negative version of something squared, okay? When I square something, it's always positive, right? But if it always has a negative leading coefficient, it is always negative. If you want to see that in detail, pick out some test points, plug it in, you'll find this is always negative. How do we interpret this? The first derivative is negative on this interval, and it's negative on this interval, 2/3 to infinity. So our derivative is always negative, except at 2/3. That's when our derivative is 0. We have a momentary slope of 0. Okay? So let's plug in our findings. there is no interval of increase, only intervals of decrease. So as we discovered, it's decreasing from negative infinity to 2/3 and 2/3 to infinity. Okay, let's put that information on our graph. I'm not going to draw the graph yet, I'm just going to give myself some guidelines. So if I complete my scale here, 2/3 is about right here. Okay, and I can say to the left of 2/3, the graph is going to be decreasing, and to the right of 2/3, it's going to be decreasing, except for a temporary little blip there at 2/3. Okay. Next, it's asking us for inflection points and concavity. This information comes from our second derivative. Again, this is a great problem because it helps you understand when am I using first derivative, when am I using the second derivative. You'll find the process here is the same. I'm just using a different derivative. Okay, so if our first derivative was negative 9x squared plus 12x minus 4, our second derivative is negative 18x plus 12. All right, set it equal to 0 as we did our first derivative. And this guy is just a little linear function, so we can solve for x directly. Subtract 12 from both sides. Divide both sides by negative 18. We'd end up with positive 12 over 18, which reduces to, let's see, 6 goes into 12 twice. 6 goes into 18 3 times. So our potential inflection point here is x equals 2/3. Okay? It's kind of like the previous critical number, but this one's giving us different information. So let's put our 2/3 on our number line. That's the only one we have to consider. It divides our number line into two intervals. Remember, our second derivative only had this one factor, so it's going to determine the sign or the concavity on each interval. So if I choose a test point less than 2/3, let's say 0, I would discover this factor is positive. A positive second derivative indicates the original curve is concave up on that interval. Okay, same thing on the right side. Choose your favorite test point bigger than 2/3. I'm going to use something easy like 1. If I plug 1 into this factor, negative 18x plus 12, I would discover the result is negative. And remember, a negative second derivative indicates the graph is concave down. So concave up from negative infinity to 2/3, concave down from 2/3 to infinity. Also notice something very important. At 2/3, the graph is changing concavity. It's going from concave up to concave down. There's a bend at 2/3. That means x equals 2/3 is the x value of our inflection point. Okay, let's transfer this to our review worksheet. Our inflection point has an x value of 2/3. We don't know what the y value is. We'll calculate that here in a moment. It's going to be concave up from negative infinity to 2/3 and concave, did I get that right? Yes, concave down from 2/3 to infinity. Okay, I'm going to transfer this to our graph. On the left side of 2/3, it's concave up. On the right side of 2/3, it's concave down. Okay, so net x equals 2/3 is not a max or a min, it's an inflection point. To find its corresponding y value, we need to plug 2/3 into the original function. So I need to calculate f of 2/3 so I'll know where to put this point on my graph. So I'm replacing all the x's with 2/3. And I'll evaluate that very carefully with my calculator. there it is. So we have negative 3 times 2/3 raised to the third power plus 6 times 2/3 squared minus 4 times 2/3. Make a little correction here. Insert that parenthesis. And finally, minus 2. I want the result to be displayed as a fraction, so I'm going to do math number 1. We get negative 26/9. Okay, now that I understand where to put this on the graph, I'm going to go ahead and approximate that as well so I can get a visual, negative 2.9. Okay, so the exact value is negative 26/9, but I'm going to think 2/3 negative 2.9. So I'll know about where to put it on the graph. Okay, so let's come over to our graph. And 2/3 negative 2.9 is about right here. I'm going to label it exactly, locate it approximately. This is my inflection point. Okay, now we just have to coordinate all of this information. Left of 2/3, our function is going to be decreasing and concave up. So decreasing, concave up. To the right of 2/3, the function is still decreasing, but now it bends shape. It's concave down. So here it's going to bend and turn. Okay, so at a very, very short moment in time, it's got a slope of 0. It's decreasing concave up. It changes concavity here and decreases to go concave down. All right, you can certainly check the graph with your calculator. I do hope you now see the difference between analyzing the first derivative for increasing, decreasing, and relative extrema, and analyzing the second derivative for concavity and inflection points. Same process, same sign graph in each case, different information obtained. All right, hope this is helpful. Hang in there and keep studying.